Hello, my friends. It's the MoNaCo here with our last, you heard it last, homework video in atomic theory. We are going to be focusing on the behavior of the electrons today, the ground state versus excited state conditions of electrons. Yesterday we did, or rather last video, we did how the electrons behave around the outside of an atom, how they fill in the principal energy levels, but now we're going to be focusing on how they actually behave within the energy level. So you should be able to distinguish between the ground and excited states of electrons and orbitals around an atom or ion today. Also, identify electron configurations as being excited or ground state. You should be able to describe the behavior of the electron when it absorbs and releases energy as it travels in the orbitals around an atom or ion. And this is the most important part, always a part 2, part 3 question on our tests here, is that identify an element based upon its Balmer series. That's the emission or absorption spectrum that's created when these electrons behave here. And here's a couple examples of the absorption and emission spectrum of hydrogen. Those lines that you see in the emission spectrum down here are related to the transits or the moving of electrons around and through and between the principal energy levels of that particular element. It's like a fingerprint that you're going to be able to see. So how does an electron behave when it's just orbiting an atom? Well, electrons are moving at close to the speed of light, and they want to do that in the lowest energy state possible. So they try and fill in the principal energy levels or the orbitals that are closest to the nucleus first. But sometimes a quanta of energy come along and it's absorbed by the electron and increases the energy of the electron as it moves. If you think about it like this, it's like some energy comes in, like you heat up this atom, and the electrons, since they're on the outside of the atom, get excited. They're the ones to absorb the energy. And so going from the lowest energy state closest to the nucleus, they might have to jump up to the next energy state. It's kind of like stepping on the gas. You throw a bunch of energy into an atom, the electrons get excited and move faster, and they move away from the nucleus when they move faster. Okay? In this scenario, the electron moves up to a higher principal energy level, and that's called excitation or absorption. Okay, so the excitation right here is when the electron absorbs that energy and says, hey, party, I'm going up top. I'm going to go up here and hang out for a while. But the story is that, you've heard the thing, what things that goes up must come down. What goes up must come down. Well, certainly is true for electrons. So a short period of time later, after that electron jumped up to the excited state, nanoseconds really, the electron realizes that, hey, I can get rid of some energy. I can slow back down and get closer to the nucleus again. So it does that. It sheds that extra energy. And you can see here is it might transfer between a few different excited states before it really does the big boom emission and drops back down to the ground state. So this is called electron relaxation or emission. So what happens when that electron drops back down is it absorbed energy to go up. Well, it's got to get rid of that energy to come back down. And while it might have absorbed heat energy to go up, as it comes back down after it makes a few hopscotches, it jumps back down and it actually releases that energy as light. And this phenomenon allows for many models of modern technology to be commonplace, like, well, I don't know, light bulbs or smartphone screens. That is what's happening to the electrons here. So ground state versus excited state. Neon, the ground state electron configuration right here. 2, then 8. 2 electrons in the first principal energy level closest to the nucleus, 8 electrons in the second principal energy level slightly outside of the nucleus. That is as closely packed as those electrons can get. This is closely packed. Now, an excited state situation for neon, or an excited state electron configuration, would be where you take one of those electrons, doesn't matter which one, and you bump it up to the next energy level on the outside. You actually create a new energy level for it to be in there. And you can see that it's a 271. If you count, the first principal energy level is still filled up, but the second one has only got it's got 7 on it. It's missing an electron. That electron just kind of went, I'm going to go hang out up here for a little while after I absorb some energy. So that's why we create this new electron configuration. And in the case that you think about it, this is loosely packed. But you're not going to recognize if it's tightly packed or loosely packed if you don't know that your basic electron configuration should be 2, 8, 8, or the lowest packing order there. So notice that one electron from the second orbital has moved to the third orbital. And it stays there for a few nanoseconds and falls back down. So the ground state is electrons in the lowest energy configuration is possible. The configuration is found on the periodic table. So all of the periodic table electron configurations are in the ground state. The ground state electron configuration for lithium is 2-1. Yeah, that's extra information for you there. Excited state. Electrons are found in a higher energy configuration, basically any configuration that's not found on the periodic table. So the example would be an excited state electron configuration for lithium could be 1-2 or 1-1-1. It still has 3 electrons, but they're not in the closest packed orientation anymore. They're looser. They've moved up, moved out. They've absorbed energy. They've become excited. So we're going to decide if things are excited or ground state just by looking at the electron configuration now. Okay, and remember, electron configuration should go something along like this. 2, then 8, then 18, and then 32. That's the max. So this is the max number in each ring for the ground state scenario. So I'm going to kind of compare back to that when I'm deciding if it is ground state or excited state. So 111, that's definitely excited. 273, well, that should be 282, so that's excited because one of those electrons has been moved up. 282 is definitely ground. 2882 is ground as well, but I want to point out that that level right here could hold 18, so it's a little gray area. 28176 is excited because that would have been 28185. Here's 28188. That is ground. And then 26181. Since this 6 right here is not an 8, we have to say that's excited. And 251832. Well, this 5 right here should be an 8. Therefore, it's excited. Okay. The other way to look at these is you could go through and instead of dealing with the whole max number and memorizing that, you could literally just pull out your periodic table and try to find an element that has the electron configuration 111. You won't find it. Therefore, it must be excited. You could try and find an element with a configuration of 273 with your periodic table. But nope, it's not there. It's excited. 282, on the other hand, I can find that. That's Mg. So that must be ground state. That matches, so it must be ground state. 2882 also exists on the periodic table, which is why I didn't like it before. So it's calcium. So that's also ground state. Okay. So I'm just showing you the second way to do it. 1, memorize what pattern the electrons fill in. 2, play the matching game on the periodic table. 28176 doesn't exist on the periodic table, I don't believe. I know this pretty well. Got to look here. 281815, 28. Nope, there's no 2817, so that's got to be excited. So you can see that some ways matching to the periodic table is easier. It's a little more time consuming though. All right. So let's move on here. So the greater the distance from the nucleus, the greater the energy of the electron. When the ground state electrons absorb energy, they jump to a higher energy level or an excited state. Okay? This is very unstable and it is a very temporary condition where the excited electrons will rapidly fall back down or drop to a lower energy level. They want to get packed in closest to the nucleus because that's the lowest energy scenario. When an excited electrons fall from excited state to the lower energy level, they release energy in the form of light. That is not necessarily the same type of energy that they absorb. Typically, they absorb heat or electrical energy or something to that effect, and they release light. But the ground of the excited state is where energy is absorbed, and dark line spectrums are produced. This is like the images, the picture, the spectral fingerprint of that particular element. For the excited to the ground state transition, energy is released, and the bright line spectrum is produced. So there are two scenarios. There's the dark line spectrum where you have the full spectrum that's got black line gaps in it, or the bright line spectrum. And the bright line spectrum is the one that we usually deal with on our tests in this class. Okay, so here's an example of a dark line and a bright line spectrum. So the dark lines show the specific wavelengths of lights that are being soaked up by the electrons in that particular element. Hydrogen soaks up 1, 2, 3, 4, 5 different energies of electron. And therefore, since it soaks them up, it also has to release them. The bright lines are when that element, hydrogen, releases the energy that it soaked up. It comes out at those specific lines. So if you overlaid the hydrogen absorption spectrum and the hydrogen emission spectrum, it would create what we call the continuous spectrum, or what you get from, you know, the red, orange, yellow, green, blue, indigo, violet, Roy G. Biv, the whole spectrum of light. Now, the Balmer series is what we call that, and that's electrons falling from the excited state down to the second or so energy level, give off visible light. We call that the bright line spectrum, like I'm saying, or visible light spectrum. The different elements produce different colors of light or different spectra. Why? Well, because they all have different number of electrons and therefore different orbital transitions that can occur. These spectra are unique for each element. It's like a human fingerprint. Everybody's is different. Well, hydrogen's emission spectrum is the same for all hydrogen, but different from helium, lithium, beryllium, etc. We use the spectral lines to identify different elements. This is actually how they can tell that other planets in our universe might be habitable. They look at the planet through a telescope and detect the light that's coming off of it, and they can see the light that comes off of it. It's got a spectral fingerprint that says there's oxygen and water in the atmosphere. That's how they find exoplanets for potential colonization. So in the practice, you're going to have to identify which elements has a ground state or which element has a excited state just by looking at the configuration. Also, I'd like you to give one possible example of an excited state electron configuration for oxygen. I'll tell you that the ground state for oxygen is 2-6. All right. And there's some more practice here. When atoms of an element in the ground state absorb enough energy, some of their electrons may fall up. Okay, so you're going to answer your Regents level questions yourself. Okay, there's quite a few of them here, but they're all in your homework packet. And this topic is definitely very, very important. I want to point out on number 8, though, that gas A, B, C, and D, these pictures represent the amounts of the lights that are given off. And it's asking what gases are present in the unknown mixture. The best way to do this is to take the unknown and trace up until you hit one of the options. Okay? See how I'm tracing up until the lines match? The lines will always be set up for you like this so that this can be done. So if you notice, the unknown mixture has elements from gas A, because those lines were present in both, and has elements from gas D. It does not have gas C or gas B because we don't see lines like this in there. Okay, we don't see those, therefore they are not present. Okay, they're not present in that particular mixture. So at this point now you should be able to understand how electrons behave, jumping up by absorbing energy, falling back down, releasing it, and as a result, the Balmer series can be used to identify elements in an unknown mixture. Okay, so just keep all that in mind. Thanks for watching. I know this video is a little bit longer than usual, but that's because it's a very, very important topic. Thanks, have a good